let's get it. Okay. Excuse me. Collision theory, catalysts, and enzymes. So these all tie back into the graphs that we were making of exothermic and endothermic reactions. So that is what's going to come back here. But we're quickly going to talk about collision theory, which talks about theory of how reactions happen, and that has to do with colliding, that particles collide, and once they collide, they can react. And then we're going to talk about catalysts and enzymes and how they can speed up reactions. Okay, so what is collision theory? Collision theory basically means that for a reaction to occur, let's say we have this dude over here and this guy. And what can happen is that they react and they become one, like this. Can that happen if they're not colliding? No, they can't just fuse into one another without actually being into contact. So collision theory states that there has to be a collision that happens between these two. So they are colliding here with their kinetic energy, their temperature, if you remember. And if this is successful, if there is enough energy in that collision, they will then fuse into their products. So then in this case, this would be our reactants and turning into our products. Yeah? So collision theory states, and pretty logically so, that you cannot react with something unless you are in contact with that something, right? You cannot react with water if water is 10 kilometers away from you at the sea, because then how are you going to react with water? You're not even in physical contact with it. That is what collision theory states. You need to collide with something in order to react with it. And there are some statements that come with it that we know that each particle has a certain kinetic energy, right? Every particle is moving at some speed. That can be slow, that can be super fast, that can be medium, but every particle is moving because it has a temperature. So this guy has a high temperature, let's say 100 degrees, this guy a 0 degrees temperature, and this guy maybe a 10 degrees temperature, right? Every particle has kinetic energy, has a temperature. So it's moving at different speeds. Then it has a second statement that says that each particle has a chance to collide, which is true. Let's say, so this is that point. Let's say each particle has a chance to collide. It's not true. Yes, that is true. Let's say we have a box over here where I have imprisoned 3 red souls for my own viewing pleasure, and these guys are just bouncing around the place. Eventually, they will bounce into each other. Is that certain? And when will that happen? I don't know, but it has a chance to collide. I know that for sure. If these keep moving, eventually there will be a collision of the two, right? Eventually they will collide. There's a chance of that happening, and you can increase or decrease that chance. For example, if I had more particles here, there's going to be a higher chance that there is a collision, correct? So that is the second statement, that, hey, we know each particle's moving, coolio, because it has a temperature, and we know that if these particles are moving, that there's going to be a chance that they're going to hit each other. Yep. And then we have point 3, that these two kind of combine, that if the energy of our particles is high enough at collision, a reaction can occur. A reaction can happen, correct? So, okay, every particle is moving. Let's draw 2 particles here that are moving. They have a chance to collide. And now the third point, if the energy of particles is high enough at collision, a reaction can happen. So let's visualize that. Let's say these two are going at a slug speed toward each other. And then here they come and they slightly bounce into each other and then just go along their day. There was almost no energy in that hitting of each other. There was a collision, true, but that might as well been like two tiny mosquitoes bumping into each other. There is not enough energy in this collision to have a reaction. Whilst if we have two particles that are zooming by at insane speeds, so let's say we have two particles here that are moving at incredible speeds towards each other, and once these two hit, they are going to collide with so much energy that they can react. Yeah? So that is, if the energy of particles is high enough, at collision, a reaction can happen, right? Because when you collide with someone, bang, you can or cannot react. So if you run into someone hard enough, you're going to fuse into two with them at some point, right? You need to have enough energy as a particle when you collide with something to overcome that activation energy and actually react. That is what it says. So if we now relate this to our graphs a little bit, here we go. This is one, and this is another. So what do we see? Main difference here, I hope. Well, this is not perfectly drawn. There we go. The main difference here is that our activation energy is different, correct? One of them has a lower activation energy than the other. So what does that mean for our collision theory? Here, this means that there needs to be a huge amount of energy in our particles colliding for it to actually react. There needs to be a high amount of energy in that collision for them to react together. Whilst if we have a low activation energy, even if they just slightly bump into each other, that is going to be enough energy in collision to cause a reaction. Yeah? So maybe this helps you visualize a little bit about collision theory and how that works with colliding and having enough energy at collision. This third rule. If the energy is high enough at collision, a reaction can happen. Okay, so we call this, when two particles bump into each other but there's no reaction, we call that an ineffective collision, because it is ineffective at causing a reaction. That's an ineffective collision. Whilst if we have enough energy to cause a reaction, that one will be called an effective collision, because what? It was effective at causing a reaction. Yeah, so that's two forms of collision in collision theory. Okay, now we have the standards laid out. Let's draw a box so that we can test some rules about collision theory. We have our three little boys in here, and they have a certain speed, right? They're moving. What factors in collision theory can affect the rate of reactions happening? Okay, and remember, when does a reaction happen? It's if two particles collide with each other at a high enough speed, and then they can have an effective collision and react. Okay, one of these factors will be your temperature. Because if you remember, what happens with particles and their temperature? Let's give this one a low temperature. That means it has a low kinetic energy, and so it doesn't move that quick. Let's give this guy a high temperature, aka high kinetic energy. That means it's moving very quickly. So now let's apply this rule into our box. Here we see that these particles have a low amount of energy. They're not moving quickly, so they have a low temperature. So they're going to be bouncing around. First of all, there's going to be a low chance that these bump into each other because they're moving so slow, correct? So that already, they're moving slowly, so they can less quickly bump into each other. And once they bump into each other, it'll look a little bit like this. They have little energy when they bump, they come together and they just kind of bounce off each other because there's so little energy within that reaction. Now let's imagine I heat up this room and all these particles are going to be starting to zoom everywhere. Once they collide now, first of all, are they going to collide more often? Yes. And when they collide, is there going to be more energy? Yes. So is a reaction more likely to happen once they bump? Yeah, 100%. Yeah? So this is how temperature can increase the speed of reaction. You can also think of it in your room. You're sitting somewhere right now, hopefully in a room. And let's imagine an imaginary particle right in the middle of your room. And it starts moving. So don't fear. It starts moving. But it starts moving at a slow speed. What's the chances that that particle is going to hit you? Those chances are pretty low, correct? And if it does hit you, is anything going to really happen? No, it's just going to bounce into you and that's it. No problem. Now let's imagine that same particle, but now it's moving at the speed of sound. So it's just bouncing around your room. Is it going to be more likely to hit you? 100%, because it's moving faster. It'll reach you eventually way quicker. And once it hits you, that one's going to hurt. Maybe going to cause an effective collision. So that's also a way to visualize how temperature affects it. Next one is the concentration of reactants. And this one is even easier to visualize. Here in our box, we have a low concentration. There's only 3 particles. Let's add more particles. Let's increase our concentration. Okay, is it more likely that particles are going to bounce into each other now? Yes, it is. So, is it more likely that there's going to be a reaction? Yes, it is, because there's simply more chance that particles are colliding all the time. So, at some point, there's going to be an effective collision, and we're going to have a reaction. Okay? So, this is how concentration increases the chance of reaction, and thus the reaction speed. Same in your room with that particle. If we have one particle moving around, and it's just traveling about, it's going to have a small chance to hit you. But if I put 6 million particles in your room, those are going to be hitting you all of the time. And there's going to be an effective collision at some point or another, right? So that is my concentration. Oh, let me switch back to my pen. What do you wanna? Same with surface area. Is if we increase surface area, so let's say this ball or one ball we increase the size of like this. Is it more likely that you are going to hit this very large surface area ball or one of those smaller surface area balls? The higher the surface area, the more likely you are to hit something. Yeah? So that is the same. Same in your room. Let's say you suddenly grow 3 times the size. Your surface area is increasing. Is it going to be more likely that that one particle in your room hits you? Yes, it is. Because there's more area that can hit you. Yeah, so surface area also increases the amount of reactions happening, the reaction speed. Another one is pressure, which is basically the same as concentration, but then for gases. So let's have these 3 particles. And now we're going to increase the pressure of the box, aka like shrink this box down. I'm Thanos. I squeeze the box down, and now I got it to the size of this little box here with the same particles in it. Are they going to be more likely to bump into each other? Yeah, because they're way closer. So we have more chances of collisions happening, so more chances for an effective collision to happen. So these 4 affect the collision theory and how they increase the speed of reaction. Temperature, because particles are moving faster. There's a higher chance that they bump into each other. And once they bump, they have more energy and a higher chance of effective collision. Increased concentration. There's more chance that you bounce into something. So more chance that you will react. Same with surface area. The larger the surface area of something, the more stuff can bounce into it. So the higher your chance of an effective collision. Pressure is the same as concentration, but then for gases. Okay, that is collision theory. Now we have our catalysts and enzymes, which is quite a quick little dive, so don't worry about this. Catalysts are basically what they do is they speed up reactions. Speed up reactions. And how do they do that? They do it by lowering the activation energy. That is what they do. Okay? So this, whoa, it was such a good straight line first. This is my reaction without any catalyst. We can see that my activation energy is quite high. So it's going to take a lot of energy to start my reaction. That's going to take some time. That's going to take time. So now, if I add a beautiful catalyst into this reaction, we add a catalyst, what's going to happen to this activation energy? It's going to decrease. Yeah, it's going to decrease. So now I need less energy to start my reaction. So it's going to be more likely to happen, right? If we go back here, if the amount needed for a collision to be effective is lower, there's going to be a higher chance that when I bounce into something, that reaction is going to happen. So a catalyst speeds up reactions by lowering the activation energy. That is what you need to know. Okay? And how does lowering activation energy speed up reactions? Because there's less energy needed to get an effective collision. Okay? So that's kind of all you need to know, is that it speeds up reactions by lowering the activation energy. Okay, boing. Now, where do enzymes fit into this? They fit into this as follows. We have this huge box of catalysts, and these are things that speed up reactions by lowering our activation energy. And within this category, within this box of catalysts, we have a smaller box that we call enzymes. And enzymes are biological catalysts. So there's just a little subdomain within catalysts that we find within biological organisms, such as humans, potatoes, stuff like that, living things, and then we call them enzymes. They are catalysts, but they are just the biological catalysts, okay? That is an enzyme. It is a catalyst. It is a biological catalyst. We just gave it a different name because biologists are vain, like me. Okay? And these catalysts, these biological catalysts, enzymes, they work in a way that we call the lock. Oh, that's a bad O. Lock and key model. What does that mean? It means that we compare enzymes and their substrates, what goes into the enzyme, reactant, as a lock and a key. So in our example, our lock is our enzyme. Okay? Just to set the tone. And our... Can I change the color here? Yes, I can. And our key is our substrate. What goes into it, a substrate or reactant. That goes into it. So how can we visualize this? Let's draw our beautiful lock, our enzyme. So here we have our enzyme that looks like this. Cool. This is my enzyme. And it can do something. It can lower the activation energy. And how does it do that? Is because it binds its products, brings them close together, and makes the reaction easier. Okay. And this guy can only bond with these two green balls. They go in. This is my substrate. They go in. They can perfectly fit into here because that's how the enzyme is shaped. They react, and then they come out fully done and dusted, and the enzyme is still intact. So the enzyme stays with us. It doesn't get used up. It's still there. Okay, cool. So let's take this enzyme, and it can do this. If there's two green balls, it can help them react. But let's now say these two want to react. They want to try to get in here. Well, that's not going to fit because this enzyme's just for these green balls. So I can't do anything here. And that's what the lock and key model means. It means that an enzyme, like a lock, can only fit one key. Like your door to your house. You have a lock. I don't have a key to it. I have a key for my own lock. You have the only key that will work in your lock, in that enzyme. So an enzyme can only speed up one reaction. It cannot go around everywhere and do this reaction, then another one, then another one, and then another one. No, that doesn't work like that. We have different enzymes for different reactions, different substrates. The enzyme is a lock, and only one key can fit into it. Only one substrate can fit into our enzyme. Yeah? So these yellow squares, tough luck buddies, you need to find a different enzyme. You need to find your lock. And let's say that might be this enzyme that looks a little bit like this. So if they try to get into here, this is now the key, our substrate going in, and they're like, oh, okay, this enzyme, this lock fits us. And it can only fit us. If we, again, have someone else knock at the door, these two triangles that want to react, well, neither of these enzymes are going to be able to do that. These locks do not fit this new triangle key. So lock and key model basically means that one enzyme can only speed up one reaction with one substrate. It doesn't go around, it's very monogamous. It has only one key, and that's it. And think about your own door and your own key. There's a lock on your door, and only your key, your substrate, can open that door. If I try to enter your house with my key, that's not going to happen, because that enzyme, that lock, can only work with your key. Cool. That's kind of all you have to know with reactions of catalysts and enzymes. So catalysts, they lower activation energy. An enzyme, we just call it, it is a catalyst, but we have a different name for it for biological catalysts, which is enzymes, and they function on this lock and key model, that one enzyme can only fit one substrate. It can only help speed up one reaction. So that means in our body, we have a metric ton of enzymes, because there's so many different keys in our body, so many different substrates, we need that many different locks for it. Okay, that's that. Oh, beautiful. Okay, thank you, bye.